So now that we have shown the historical global temperatures, and that these temperature records show that the average temperature have been within limiting ranges, and that is continuously changing, we of course, or scientists wanted to measure or to be able to make predictions, right? So to be able to make predictions, they needed to have a basic mathematical model to base these predictions, right? To predict different scenarios, right, in the future. So mathematical modeling of global climate and predicting the impacts of changes in key environmental parameters is an extremely important but difficult task. So such models range from very simple ones, so black box models, and there are other more complex models that also involves regional scales, for example. So the most simple way to start a climate model is to base the model on one parameter that has been measured in the past. And one key parameter that we've been discussing is temperature. So this can lead us to have a model that is actually based on balances of incoming energy and out and energy leaving the Earth, and that's the basis of the basic zero-dimensional energy balance model that we're going to discuss now. So in this model configuration, we're not going to consider the latitude, the longitude, the altitude, and the time. Okay, that's why it is a zero-dimensional, right? And also zero because it's a balance is based on a steady-state condition balance, right? So we're going to start by looking at how much radiation from the sun arrives just outside the Earth's atmosphere. And this is an average of the solar intensity, and this is called solar constant. And it's been determined to be 1,370 watts per square meter. So a simple way to calculate the total rate at which energy hits the Earth is to know that all the flux passing through a hoop having a radius equal to that of the Earth and place normal to the incoming radiation strikes the Earth's surface. So if we have the radio of the Earth and we determine the area of a circle based on that, we can actually predict how much energy in watts is inciding the Earth. So it is based on, of course, the circle equation and the constant that I was talking about. Some of the incoming solar energy that hits the Earth is reflected back into the space. Such reflected energy is not absorbed by the Earth or its atmosphere and does not contribute to the heating. The fraction of incoming solar radiation that is reflected is called albedo. And please keep in mind this concept because it's key for understanding global warming. For the Earth, the global annual mean value is now estimated to be about 30%, 30 to 31%. This has been estimated using satellite measurements accumulated since 1970s, where they have actually measured the amount of energy that is being reflected from the Earth. And it depends. Later on, we will discuss this in terms of the wavelength of the absorption of this energy, and so it is connected to the reflection. Just to give you a hint on this, I will tell you that if Earth will be completely covered on ice, its albedo will be about 84%. But on the other hand, if the Earth will be covered with dark green forest canopy, the albedo will be about 14%. All right, now you see the range, and now you start thinking how is this measured. So now that we have estimated how much energy is inciding from the sun, now we're going to do the balance on the other side of the equation. So it is the energy of the Earth that sends back to space. all right? And for this, we're going to use this albedo constant. So the only way for the Earth to get rid of energy is by radiation. So we are not going to use, or we're not going to estimate conduction or convection for this, because it doesn't have a role here on the energy that goes back to space, only radiation. Every object radiates energy at a rate that is proportional to its surface area times its absolute temperature raised for the fourth power. For this model, we will assume the Earth as a black body, which is it will radiate as much as any object with the same temperature and area possibly. So it is. So we're talking that emissivity is equal to 1. Okay. We also assume that it is isothermal. That is, the temperature is the same everywhere on the planet. And how are we going to distribute this radiation? We're going to redistribute this radiation in terms of a spherical object. So then we need to know how the area of a spherical object is being calculated. So then the equation for the energy radiated back to space by Earth will be equal to a Stefan Boltzmann constant, who is the one who has helped us to estimate this radiation. And if you have done some work with energy balances, you are familiar with this equation, the Stefan Boltzmann equation, and the constant. And then we're going to have a component that is related to the spherical area, and then the component of the temperature elevated to the fourth power, right? And this temperature is the Earth's effective black body temperature. If we go on the assumption of steady state conditions, that will mean that what goes in equals to what goes out. We can equate the rate at which energy, energy from the sun is absorbed, with the rate at which energy is radiated from Earth back to space, right? So we now have the two equations combined. So what goes in equals to what goes out. And now we're going to solve for the temperature, for TE, which is T effective. And now we come up with this equation that tells us that the temperature of the Earth, the average surface temperature, should be about minus 19 degrees Celsius. Now, you can tell me that of course this is not true, right? And if this will be the case, we will not have a life as we know it now, and these ecosystems and this way of living in the Earth, right? So actually, the actual value of the Earth's average surface temperature is currently about 15 degrees. Now, I must tell you that for these equations, we always have to use Kelvin, but I'm going to have the discussion based on Celsius, all right? So while we are off by only 12%, which might seem a modest error, in terms of life on Earth, this is terribly wrong, right? So to find an explanation of why the Earth is not that cold, we need to include a key factor that we're going to discuss in our next session, which is the greenhouse effect.